All right, thank you, Chris. It's a great honour to be asked to give the annual Webb lecture because I've known Webb's celestial objects for common telescopes since I was 15, when I got a second-hand copy of the paperback edition by Dover Publications, so I know it well as a sort of both planetary and deep sky guide. And I was also editor of the Royal Society's journal for a few years, and so it's a pleasure to do this. And sorry I can't be with you in person. I actually agreed to give this talk a year ago, and I was offered a date in October 2020 and then a date in March 2021. So I said I'd better opt for 11th of March 2021, since I want to be well clear of this coronavirus pandemic. But here we are, still a year. Anyway, it's I'm currently based in Cambridge, not only for social distancing reasons, but also because that's where the Greenwich Observatory archives are, and that's where I'm doing the research. And I'm researching basically the 20th century history of the Royal Observatory. And this talk is still therefore a sort of work in progress, and I'll focus on the Royal Observatory in the 1900 to 1914 period, which hasn't been hugely researched. So if I can have the next slide, please. I'll start with a little historical background.
It might take a second, Lee, but just 1 second.
Thank you. Yeah, that's it. Okay, so the Royal Observatory was founded in 1675 in the reign of Charles II to solve a very specific problem with navigation. And that is, ships had no way of determining the longitude at sea and frequently got lost. And sometimes it was said that more sailors died of scurvy and starvation because of ships being lost at sea than they did in battle. But one young up-and-coming astronomer called John Flamsteed had a bright idea. He didn't invent the idea, it was known for at least before Flamsteed's time, but Flamsteed had this idea that if you could know the position of the moon and the stars accurately enough, you could use them as a clock. And with if you knew what the position of the moon would be, regardless of your location on the Earth, relative to the background stars, you would know the time at Greenwich Observatory, and therefore you could work out the difference between that and your local time aboard ship, and that would give you your longitude and position. Clocks weren't any use at sea at the time because no clock was ever accurate enough. The best clocks they had at the time were pendulum clocks, and they were pretty useless for obvious reasons on a moving deck of a ship. So Charles II appointed John Flamsteed, our Astronomical Observatory, that was the original name for Astronomer Royal, forthwith to apply himself with the utmost exact care and diligence to the rectifying the tables of the motions of the heavens and the places of the fixed stars, so as to find out the so much desired longitude of places for the perfecting of the art of navigation. Okay, next slide, please. Okay, so Flamsteed got this warrant as the Astronomical Observatory in March 1675, and then 3 months later, Charles II issued a warrant to build a small observatory within the Royal Park at Greenwich. Flamsteed, they only had a budget of £500 to build this rather immaculate building that was designed by Christopher Wren, and that did not include a budget for any instruments. So Flamsteed had to buy his own telescopes and measuring instruments. So There is nothing new about underfunding of British science. But over the next 40 years, Flamsteed carefully made measurements of stellar positions and also of positions of the moon to a far greater accuracy than had ever been achieved before. And he completed this star catalogue by the time he died in 1719. And this showed stars down to about the 6th magnitude. Not accurate enough yet to be useful for determination of longitude, but getting better and better all the time. Okay, the next slide, please. The problem was given more urgency in 1707 with the greatest disaster in British naval history, when the Admiral Sir Cloudesley Shovel, that's his picture on the right here there. I don't think I'd want to argue with Cloudesley Shovel or get on the wrong side of him, but anyway, he and his fleet of about 2,000 sailors perished off the Isles of Scilly, while their ships were massively off course because they didn't have an accurate position. And in 1714, Parliament voted a bill for providing public reward for such person or persons as shall discover the longitude at sea. And this offered a prize of £20 for a solution that was, in their own words, practical and useful at sea. And the government appointed a committee of the scientific men and naval officers of the day, which was known as the Board of Longitude, although the board didn't actually meet until the 1730s. Next slide, please. Okay, now this Flamsteed was succeeded by a succession of illustrious astronomers royal, notably Edmund Halley of Halley's Comet fame, and James Bradley. And in the meantime, positions of the moon were becoming more and more accurately known, thanks partly to the work of Isaac Newton and his Principia, whose theory of gravity allowed the moon's position and motion to be accurately calculated. And also you had Tobias Mayer in Germany, who applied Newtonian mathematics to produce really accurate tables of the moon's position. And of course, the star and lunar measurements at Greenwich were getting better and better all the time. You can see in the picture of the right is a quadrant built for Edmund Halley by George Graham, who's one of the top instrument makers at the time. Now, Halley's successors eventually were James Bradley, then Nathaniel Bliss very briefly, and then finally in 1764 Neville Maskelyne. And Neville Maskelyne became Astronomer Royal at the right time, because by then the lunar tables were getting accurate enough, and he'd only been Astronomer Royal for about a year when he published the first edition of the Nautical Almanac, which gave these essential lunar and stellar tables that enable sailors to determine their longitude. And this Nautical Almanac has, of course, been issued every year ever since, though it contains rather different data in its modern form, as you might expect. Now, the lunar distances method worked, but it was really complicated because, although it seems very simple, the lunar distances method, and as the way I've described it, in practice it involves lots of intricate mathematics to determine one longitude position. So you've got to be a navigator on board a wooden sailing ship, the deck heaving up and down, and probably the French shooting at you or something like that as well. And you're trying to solve problems with logarithms and trigonometric equations. But fortunately, a simpler method of finding longitude came on stream later in the 18th century. Next slide, please. Yes, now, most famously, most of you will have heard of John Harrison, who in the 1730s developed the first really reliable clock that gave accurate time at sea. And he received a bit, £2,750, of the longitude prize money to develop his invention further. And 30 years later, he finally came up with the Model H4, as it became known, and that was a large watch, the size of a tea plate. And you can still see it on display at the Royal Observatory Museum at Greenwich to this day. And this was successfully tested on a voyage to the Caribbean and found to be more than accurate enough to determine a ship's longitude to within a few nautical miles. But the Board of Longitude weren't satisfied with it because the invention wasn't easily reproducible. And Harrison did not get paid the balance of his prize money until 1773, after a fifth watch called H5 was successfully tested. And by that time he was 80 years old, so he only had 3 more years left to live and enjoy the prize. But the longitude thing also showed up the need for a standard time, and the Greenwich meridian gradually became adopted as the standard meridian of longitude for shipping. Next slide, please. Now, by the time George Airy became Astronomer Royal in 1835, the longitude problem had been largely solved, and indeed the Board of Longitude itself wound up. However, there was still great use for the Royal Observatory. This is partly because many ships were still using the lunar distances method, and in any case you had to have this standard time with which to set their chronometers for those ships using the chronometer method to find longitude. And Airy dramatically overhauled the equipment at the Royal Observatory, which had fallen into a state of disrepair and disarray by the time he became Astronomer Royal. And the biggest instrument he installed, the most important instrument, was the Airy, the transit circle, which took transits of stars in order to determine time for the time service, as well as produce catalogues of stellar positions. And Airy was motivated by a very, very strong sense of public utility. That's what he believed he was paid to do, was to serve the public. He was an early example of a scientific civil servant. And so he quickly took up the opportunities presented by new technology, such as the electric telegraph, because Airy realized that this could allow the Greenwich time to be transmitted all over the country. And this was a technology that came at exactly the right time, because the development of the electric telegraph was pretty much concurrent with the development of the railway. And railways needed an accurate standard time in order for the trains to run on time and not crash into each other, indeed. So in 1852, the Greenwich time was legally sanctioned as the railway time for the entire expanding British railways network. And in 1880, Greenwich time became civil time, or the legal standard time. So that was, you know, if there was a court case, that was the Greenwich time was the legal time that was used. Although by then, by 1880, Greenwich Mean Time was the kind of de facto standard time. It's curious to think that 200 years ago, different cities across the UK had different times, because they all had their own local time determined by the local transit of the sun. But with Airy's Greenwich and the telegraph and the railway came this sort of national standardization. And Airy also led the way in determining longitudes around the world, and based on Greenwich time, not only in the British Empire, but with other countries as well. And quite famously, the longitude difference between Greenwich and Paris observatories was determined by the telegraph. Next slide, please. And that's a picture, a drawing of the Airy transit circle looking in a northerly direction at the Greenwich Observatory. Next slide, please. And that's the part of Greenwich Observatory taken in a sunny summer's day. The building on the left underneath the dome, that's where the transit circle is located, and that's where the meridian is located. Next slide, please. And that's a close-up showing the entrance to where the sign is marking the prime meridian of the world. And of course, you can always go and stand on the meridian line. But that line wasn't actually marked out until the 1960s. It's not as historic as it looks. Next slide, please. And this is also a public clock. It's actually a modern replica. The original destroyed during World War II, but this was a public clock that was installed by Airy that gave the standard Greenwich time taken by telegraph from the master clock inside the observatory, but that was on the front gate and could be viewed by the public. And indeed, it was taken, that was used by the lady called Ruth Belville, the Greenwich time lady, who took a chronometer with her from Greenwich to the watchmakers of London, who gave her the accurate time. Next slide, please. Now, George Airy, with this new equipment, turned Greenwich into a factory of astronomical observations. And as I said, Airy's priority was always public utility rather than astronomical discovery. And this explains, at least partly, Airy's inaction or alleged inaction over the discovery of Neptune in 1846, which Britain basically was beaten to it by the Germans and the French, even though a British mathematician, John Couch Adams, had calculated a predicted position for the new planet. But Airy was robust in his view that that was not the job of the Royal Observatory. Indeed, he did an awful lot of non-astronomical work for government commissions on things like railway gauge or the sale of gas. Airy did bow to some pressure to modernise the equipment when he installed the so-called Great Equatorial in 1858. This was a 12 3/4 inch refractor, which made observations like planets and comets. And also very early in his career as Astronomer Royal, Airy installed the Magnetic and Meteorological Department, which, although that was not only utilitarian, but geomagnetism in particular, Airy thought it needed a long series of continuous observations, and he thought that's the National Observatory was the best place for that type of observation. So that was an early example of organised geophysical observations in this country. Next slide, please. And that is a watercolour by one of Airy's daughters showing the Magnetic and Meteorological Observatory in the mid-19th century. You can see in front of the wooden building a shade for thermometers. That's a kind of precursor of the Stevenson screen. And the building itself is made of wood so that there was no magnetic interference with the magnetometers inside. And that huge great pole where you can see a little man climbing up it, that is an electrometer for measuring atmospheric electricity. Next slide, please. Now, Airy retired in 1881 at the age of 80, and he was succeeded by his younger chief assistant, William Henry Maloney Christie. Now, William Christie had somewhat different astronomical interests from Airy, and indeed, astronomy and the wider world had somewhat changed by 1881. Christie was interested in a new type of astronomy known as physical astronomy, or astrophysics, as it later became known, which was not so much about measuring the positions of stars for navigational purposes, as the traditional work was at Greenwich, but studying the properties of stars and other celestial bodies themselves. And this new science of astrophysics was made possible by two new technologies that had appeared. One was spectroscopy, which allowed you to analyze starlight for its chemical components, and the other was astronomical photography. And Christie, in his first annual report as Astronomer Royal in 1882, said he wanted to free up time at the observatory for equatorial observations, that is, observations with equatorial telescopes like planets, comets, properties of spectroscopy, etc., because the observatory can hardly maintain its position as a national institution if it gives no attention to objects which from time to time excite the interest of the astronomical world. And in the 1890s, Christie oversaw the construction of a new building called the Physical Observatory, or the new Physical Observatory, which I'll talk about a bit later. Next slide, please. Now, the first big new telescope that Christie installed was the 28-inch refractor, which is still in the same building at Greenwich today. And he, in order to get the biggest refractor he could afford, he made economies elsewhere, and one of them was mounting it on the same mount as the old 12 3/4-inch refractor, which was actually robust enough for a much bigger telescope, and it's still on this English, so-called English mounting, which was originally designed by George Airy. And the old 12 3/4-inch Airy refractor was too small for stellar spectroscopy, because the splitting a star light up into a spectrum makes it really, really faint. So you need a big telescope to get proper spectra of stars. But Christie was also concerned with the prestige of the Royal Observatory and wanted a refractor, in his own words, comparable with those of other first-class observatories, meaning national observatories around the world, such as Paris, such as the US Naval Observatory, such as Pulkovo in Russia. And a 28-inch, Christie realised, would raise Greenwich from just 31st in the pecking order to 4th in the pecking order of the world's largest refractors. And next slide, please. So the 28-inch refractor eventually went into service in 1893. And in the event, they never used it, so it's extremely small separation indeed. The old dome for the Airy refractor was no longer serviceable, and it was not big enough. So that is the origin of this strange-looking onion dome, which you see at Greenwich, which Edward Maunder described as looking like an enormous Spanish onion. But it wasn't just any old onion shape. Christie's letters clearly show that he wanted a mathematical shape to adorn the Greenwich skyline. He adopted a mathematical figure called the involute of a circle, which is difficult to explain in a few words, but it's made by drawing a band around a circle and then pulling it taut, and you get this this funny shape. And so this is probably a tribute to the fact that Christie, as well as were most astronomers royal, was a mathematics graduate from Cambridge, where he had been a wrangler. That is, he got very high marks in the mathematical tripos. And it's also a tribute to Christie's attempt to have the largest refractor, which would put it in the same league as the other observatories around the world, particularly as this was the age of the great refractor. Next slide, please. Now, Greenwich was prestigious enough to attract donations from wealthy people. Among them, this chap called Sir Henry Thompson, who was a surgeon to the great and the good, including things like people like the King of Belgium, and whom he operated on for £3,000. That's £3,000 in the 19th century. And so late in life, this Thompson was a rich man. And he had an interest in astronomy, a serious interest in astronomy. In 1890, he donated a 9-inch telescope for observing the sun that he never used. And then in 1894, Thompson offered the Royal Observatory £5,000 for a large refractor specifically for astronomical photography. So Christie ordered a 26-inch refractor with specially for photography, the lens corrected for photography, and put it on a German mount, and the whole thing was made by Grub Parsons, which had emerged as a major instrument maker for observatories across the British Empire and beyond. Grub Parsons were then based in Dublin. And 12-inch refractor as a guide scope for this new giant refractor. Next slide, please. In the meantime, a wealthy amateur astronomer and engineer called Andrew Ainslie Common had offered to make Christie a 30-inch mirror for a reflecting telescope. Common was famous for making large reflecting telescopes and using them for astronomical photography. So Christie then asked Grubb, when he was making the 26-inch Thompson refractor, if they could mount a 30-inch reflector on the other side of the declination axis in place of a counterweight. And Thompson generously offered the funding for that, and Common also offered to make the mirror for no more than his out-of-pocket expenses. So Christie effectively got 2 telescopes for not quite nothing, but next to nothing. Okay, next slide, please. Now this twin equatorial 26-inch and 30-inch reflectors were mounted in a dome atop this impressive new Physical Observatory building. Although it was a Physical Observatory, not a great deal of astrophysics was done in it, apart from with the big telescopes. Most of the building was in response to Christie's increased need for office space and libraries space and storage space for the growing volumes of observations and photographic plates. And the telescopes that crowned it were the result of these donations by Thompson and Common. So the Physical Observatory didn't come as a result of a grand plan by Christie. It was more in response to events. Next slide, please. And there you can see the Physical Observatory in its entirety. From some photographs, you might think it looks quite a grand and huge building, but it's actually quite modestly sized. You can see from the man standing at the front of the front gate there. But you can see, you can get some idea of the scale. But it's still a very fine building, and it was until recently open as part of the Royal Observatory. It was open to parts of it were open to the public. Sadly, that's not the case for now, not just for COVID reasons, but because they are actually refurbishing the interior as well. But you can still certainly walk past it and see it as you look at if you visit the Royal Observatory. Next slide, please. Okay, one of the other things that Christie expanded at Greenwich was solar physics. Now, Airy had taken this on at Greenwich in 1873 when he managed to wangle the photoheliograph or solar photographic telescope from Kew Observatory over to Greenwich, which is a bit of a story in itself. But with the Kew photoheliograph and successor instruments, Airy and his team started photographing the sun's surface. The idea was to photograph the sun's surface every day if possible, and then use the surface area of the sun's sphere covered with sunspots as an index of solar activity. Some of you might have heard of doing sunspot counts to measure solar activity. This is a slightly different method. This used the areas of sunspots that cover the sun. And Christie expanded this he realized the value of international collaboration, or at least collaboration with other observatories in the British Empire at the time, places like India, Mauritius, and the Cape of Good Hope in South Africa. Now, relying on Greenwich observations alone, at the end of Airy's time in 1881, they only managed photographs on 149 days. But by 1899, thanks to this collaboration, Christie increased it to 364 days coverage. So only one day did they not have some sort of photograph of the sun received for analysis at Greenwich. Next slide, please. Now, the head of the solar department was this chap, Edward Walter Maunder, who was a very influential and innovative astronomer in many ways, although did not really get much recognition for it in his own lifetime. Maunder confirmed what we now call Sporer's law, which shows the tendency of sunspots to descend in latitude and move towards the equator as the solar cycle progresses. So whereas at the beginning of the solar cycle, most sunspots tend to be at high latitudes, towards the end of the cycle, they are concentrated in low latitudes around the solar equator. It's all famous for the minimum sunspot which occurred in the 17th century and has been linked by some to colder winters and slower growth of trees. He also famously founded the BAA, the British Astronomical Association, in 1890. This was specifically targeted at amateur astronomers, and this because Maunder and others thought that the Royal Astronomical Society, the subscription was too high for many ordinary or at least middle class people to afford, and also the Royal Astronomical Society at the time did not admit women, whereas the BAA admitted women as full members from the word go. The next slide, please. And yes, that just shows you the butterfly diagram with not Maunder's original version, but a modern version produced by NASA, just showing the butterflies, the decrease in sunspot latitudes in tandem with the various solar cycles below. Right, next slide, please. Now, one of these early women BAA members was Annie Scott Dill Maunder, or Annie Russell as she was originally known. Now, Annie Maunder Russell had studied at Girton College in Cambridge, then an all-women college. She had studied mathematics and taken the mathematical tripos. But sadly, women at the time were not allowed to graduate at Cambridge, no matter how well they had done. So they had to settle for this certificate known as senior optime. But many of them did as well as the men, and some of them indeed would have become wranglers. And this situation wasn't changed until 1948, within living memory. So this is, one of the great social injustices of the time. But nevertheless, Annie Russell got a job as one of the lady computers who were briefly employed at Greenwich in the 1890s. And these computers, although the name suggests that they just did calculations, they also did observing. She eventually had to leave Greenwich when she married Maunder in 1895. And the two of them collaborated on the butterfly diagram, and Annie's mathematical skills became essential in demonstrating a correlation between sunspots activity and magnetic storms on Earth. And Annie also accompanied her husband on solar eclipse at the end of the 19th, beginning of the 20th centuries, and became an accomplished solar photographer as well as mathematician. Next slide, please. Now, the other big thing that Christie got into was the observation of solar eclipses. Now, the observation of solar eclipses was more or less synonymous with the new astronomy, the new astrophysics. The picture on the right shows a picture of the 1860 solar eclipse taken with the Kew Observatory photoheliograph, which was transported from Kew down to Spain, where the 1860 eclipse was observed. And that was where Warren de la Rue finally showed that prominences were a feature of the sun and not part of the moon. And astronomers then started to take an interest in what was the properties of the sun's atmosphere, or the corona, which was only visible during a total eclipse, and also the lower atmosphere called the chromosphere. And so eclipse expeditions became a standard feature of the and they were facilitated by the advent of the steamship, which transported to places reasonably quickly. So the British Empire, which provided things and places where you landed were peaceful and under British control, and so on. And the Royal Society and the Royal Astronomical Society coordinated these eclipse expeditions. Their joint eclipse committee, which, that this was a committee of astronomers which organised these expeditions. And Greenwich was heavily involved in three, especially during Christie's time. India, 1898, that's where Edward and Annie Maunder went. Then Portugal in 1900, a place called Over in Portugal, and in 1905 to Tunisia. All very good results. They didn't do a great deal of new science, of spectacular discoveries the way Warren de la Rue, but they did make progress in analysing the sun's spectrum of the atmosphere during these eclipses. But they did provide experience for the most famous eclipse expedition of that of 1919, which I'll mention towards the end of the talk. Next slide, please. Now, Christie also expanded international collaboration, not just with solar observing, but also with a object that became known as the Carte du Ciel, or the Astrographic Chart. This was very much a product of the new photographic technology. In 1882, at the Cape of Good Hope, the astronomer David Gill took some photographs of a brilliant comet that was visible that year. And he got great pictures of the comet, but he also showed, the photographs showed huge numbers of stars. And Gill realized that this would be an ideal way of mapping the stars and getting accurate star positions of many, many more stars, many fainter stars than before, because hitherto the only accurate way of measuring star positions was by these transit observations, in which you observe stars one by one, which is an incredibly slow and tedious process. And also in the 1880s, two brothers, Paul and Prosper Henry, working at Paris Observatory, had developed a large refractor which had a very good photographically corrected lens that could give wide field star images. And so Gill and then the director of the Paris Observatory, Admiral Mouchet, got together and organized, what they hoped would be an international project to map the sky photographically in unprecedented detail. It had to be international because they had to cover both the northern and the southern hemisphere. This led to a conference in Paris in 1887 called the Astrographic Congress, in which Christie, the Astronomer Royal, was one of the delegates. And each observatory that agreed to participate was assigned a zone of a part of the sky to photograph. And Greenwich was tasked with photographing the sky between declination 65 degrees and the North Celestial Pole. And Greenwich, with a bit of struggling, got funding from the Admiralty to buy a 13-inch photographic refractor and set it up on a dome on top of the old observatory. Greenwich had to take a total of 1,149 photographs, and by 1900 they mostly succeeded in doing that. There were two sets of photographs to be taken. One was photographs for the astrographic catalogue, whose stars would go down to the 11th magnitude, and another was a set of actual photographs to be distributed that would show even fainter stars going down to 14th magnitude, which would need a much longer exposure. Next slide, please. So by 1902, the photography was practically completed, but the measurement was still quite labour intensive. Photographing the stars is one thing, getting accurate measurements from the plates and allowing for errors and factoring those out was a somewhat different matter. Not so much because it was difficult, but because it was time consuming, and it required the observatory to take on additional staff, which wasn't easy. And so it took several years. But nevertheless, by 1909, Greenwich became the first observatory to, in the Astrographic project, to complete its not only its photography, but also its measurements and the publications of the star map. And it had even distributed photographic copies of the star plates to other observatories. And so, why did Greenwich get in ahead of everyone else? Really, I think it was because it was the kind of project that suited Greenwich: long-term, meticulous observations. And while Greenwich was never particularly well funded, other observatories were even less fortunate. The Vatican Observatory did complete its share, because they, like Greenwich, had access to cheap labour. They had nuns, apparently, measuring the star plates, but other observatories fell by the board, and the whole project was never completed. The catalogue eventually came out in the 1960s, the full combined catalogue of all the observatories, but the observatories never completed the photographic star atlas. And in any case, by then, the things like the Palomar Observatory Sky Survey had superseded it. But nevertheless, the astrographic chart and Greenwich's role is very important for two reasons. I mean, one is that the Greenwich astrographic plates taken in the 1890s and the 1900s give invaluable positions of stars for modern proper motion studies. Then plates taken at a later date can be compared with them, and you can measure how much stars have moved. And indeed, results from the astrographic data were eventually used in the catalogue, the base catalogue used by the Hipparcos satellite, which measured star positions in the 1990s. And also because it was also important because the Astrographic Conference, in the words of one astronomer at the time, was the first of its kind in the history of astronomy. It was the first real international collaboration. We take scientific astronomical conferences internationally for granted for now, or at least we did until March 2020, but this was a new kind of thing, because before then international collaborations tended to be between one scientist and another in a sort of republic of letters, as it was called. This heralded the modern way of doing astronomy. Next slide, please. Now, Greenwich also hit the headlines for a couple of reasons while Christie was still Astronomer Royal. Christie retired in 1910. But in February 1908, one of the assistant astronomers, called Philibert Melot, was looking at some plates of Jupiter taken with the 30-inch reflector. These plates were long exposures, which were trying to get accurate positions for two small satellites of Jupiter that had recently been discovered in the United States. But Melot noticed an extra moving object on these plates, and from measurements it was soon found that it was a new satellite that had not been discovered before, the 8th satellite of Jupiter, what we now call Pasiphae. So it's a very small moon, very faint, about 15th magnitude. So that was a real triumph for Greenwich Observatory, and also for Philibert Melot. You may think the name, his name sounds French, and you're almost right. He was actually Belgian. His parents were Belgian refugees from the war, the Franco-German War of 1870. Now, at about the same time, two other mathematicians at Greenwich, one was Philip Cowell, the other was Andrew Crommelin. They successfully predicted the 1910 return of Halley's Comet. They knew it was going to return in 1910, but nobody knew quite when it would pass perihelion. That's its closest point to the sun, or its exact position in the sky. Unfortunately, Greenwich missed out on the visual recovery of Halley's Comet. That was achieved in Germany at the Heidelberg Observatory. That Cowell and Crommelin won a competition to predict the perihelion. They predicted for 16th of April 1910, just 3 days before the actual perihelion of the 19th of April. And they were even able to conclude that this error was must have been due not to any mathematical errors on their part, but due to non-gravitational forces acting on the comet. And these forces, we now realise, are in fact caused by the comet's own motion, the comet chucking out gas and dust, and that causing some independent motion of the comet. So Greenwich became famous around the end of the Edwardian period for this new satellite of Jupiter and these comets. Next slide, please. We must emphasize, though, that the program Greenwich under Christie was a bit more traditional than it looks, because the traditional navigational work still continued at least as intensively as before. They still made transit circle observations, making a record number of more than 16,000 in the year to May 1914. And Christie also built this little, rather pretty little building on the right, which is still there, which contained an instrument called the New Altazimuth that made more transit observations and measured the parallax of the moon. They also continued the longitude difference measurements, initially by telegraph, and then they started receiving time signals initially from Paris by wireless, which after the First World War would transform longitude work and would start to make the chronometer obsolete, because when ships had wireless, then they could receive the time signal at any time. But in the meantime, Greenwich continued as a centre for testing chronometers for Admiralty ships. They also provided a time service via the time ball, which was dropped at 1 o'clock every day, and that enabled ships' captains to set or to check the chronometers on board before going on a voyage. The next slide, please. And this shows the time ball on top of the old Flamstead house. This is the oldest part of the observatory on a rather nice summer's day. I've actually been inside that turret when the time ball dropped at 1 o'clock, but it's not as scary as it sounds because it does have a cushioning device. Next slide, please. Now, all this activity required people to do it. And in 1881, Airy left the observatory with about 30 odd staff, one chief assistant who was the Astronomer Royal's deputy, 8 assistants who were kind of senior astronomers in charge of departments, and then 12 computers who did the number crunching, as well as assisting in the observing. And then you had various support staff such as gardeners, carpenters, and mechanics, and so on. Christie was always complaining about inadequate staffing, and again, out of funding, nothing new. The Admiralty were very, very slow and very, very reluctant to give him any more staff. By 1900, the staff had swelled to 53. However, 29 of these were now computers, and many of these were so-called supernumerary computers, which were basically teenage boys, school leavers, hired on temporary contracts to provide the cheap labour to do calculations and even help with the observing as well, because some of them had sort of proficiency tests on the telescopes and became qualified as observers. The most senior of the astronomers, the chief assistants, were nearly always Cambridge mathematics wranglers. The most famous one to work at Greenwich in the post-1900 period is on the right here. That was Arthur Stanley Eddington, who was chief assistant for quite a while, from 1906 to 1913. And it was widely expected that these chief assistants would either become the next Astronomer Royal, or would go on to some major prestigious post at another observatory. In Eddington's case, he took the historic Plumian Chair of Astronomy at Cambridge. Next slide, please. Now, some of this cheap labour was provided by these lady computers, of which you've already mentioned Annie Maunder. And Christie took these women on, partly, to be fair to Christie, he was very keen on the advancement of women, but also they were cheap labour when the Admiralty refused to fund more staff. They were all university graduates, as was Annie Maunder, but they were paid no more than the teenage boy supernumerary computers, i.e. not enough to live on. So most of them left pretty quickly, because women suitably qualified by that time could earn much more than working as school teachers. And two exceptions who stayed longer were Alice Everett, who worked at Potsdam Observatory in Germany and then National Physical Laboratory, and of course Annie Russell stayed until 1895 when she became Annie Maunder. Thereafter, the Royal Observatory only began to employ women again after the outbreak of the First World War. Next slide, please. Now, the Royal Observatory had its governing body, ever since 1710, had a governing body known as the Board of Visitors. And that met rather formally every year and heard the Astronomer Royal's annual report. And its chairman was always the president of the Royal Society, whoever that was at the time. So that was not necessarily an astronomer. In fact, most of the time, that wasn't an astronomer. And for the rest, there were the visitors comprised 6 fellows of the Royal Society, 6 fellows of the RAS, and 3 ex officio members, the hydrographer of the Navy, and the Plumian professor and the civilian professor. So Eddington, for example, having been chief assistant, after 1913, he became one of the visitors. And the visitors sanctioned applications to the Admiralty for funding. And on the right is a title page of one of George Airy's reports to the Board of Visitors that was printed each year at the time of the meeting. Next slide, please. Now, by the early 1900s, there were serious challenges to Greenwich as an observing site. It was no longer the sort of pretty much rural location that it had been in the days of Charles II when it started. And you see all these paintings from the 17th and 18th centuries showing Greenwich as a country location with just the dome of St. Paul's in the distance to remind you that it was actually quite close to London. And in 1889, London County Council had been established, and that incorporated Greenwich as well. So that showed you that Greenwich was part of an urban area. In 1900, a popular book about the Royal Observatory say that it of observatory far from the town. This became the inadequacy of Greenwich as a site became more publicised in August 1905 when the Daily Mail newspaper ran an article describing the Royal Observatory's current location as an anachronism and suggesting it move out of town. The Daily Mail is quite similar to what we know today. It's very patriotic, very Tory, but it was not necessarily opposed to change. In fact, it was actually supported the idea that if Britain were to keep up in a changing world, it had to raise its game. And this idea of moving the Royal Observatory was part of this national efficiency drive, as it was called. And there's quite a lively exchange of views in the Daily Mail. Some astronomers supported removal, some were dead against it, or some suggested a compromise. But it was just a brief exchange of correspondence, and at the time it didn't go anywhere. But a few months later became a much more serious challenge. Next slide, please. In November 1905, Christie wrote to the Admiralty that the London County Council was building a power station of abnormal size and with abnormally high chimneys, half a mile north of the observatory. The engines which would generated the electricity would cause vibrations which would ruin the observations of star transits. And even worse, the power station itself was exactly on the meridian. So emissions from the chimneys would cause trouble with the images of stars low in the northern sky. And Christie reminded the Admiralty that the general public, as well as the Admiralty, are directly interested through the use of Greenwich time. Next slide, please. And this shows a panoramic view of not only the first two chimneys of the power station when they were newly built, but also the rest of the skyline near Greenwich. And you can see how bad the conditions have become with the smoke and the gasometers and the industrial chimneys round about. No questions about moving earlier than 1905. Next slide, please. Now, the County Council's response was slightly predictable. Postponing construction would cost too much, as would shorten the chimneys, and they recommended that Greenwich might rearrange the instruments which are used for the observations, as if that was practical to move the Airy Transit Circle. And even more local government said that in building the power station, the council was just doing its public duty. Next slide, please. In May 1906, tests confirmed that vibrations of the 10 to 20 times the normal limit of accuracy achieved at Greenwich were seen when the power station's engines were running. One of the observers carrying out these tests was, in fact, the young Arthur Eddington. And then at the end of May, the Board of Visitors agreed that it would endanger the continued existence of Greenwich Observatory as the reference point for longitude and destroy the continuity of a series of astronomical labours undertaken for the benefit of mankind, which have extended over 230 years. Next slide, please. The Daily Mail had its I told you so moment, because it then said that the power station crisis had revived the question of removing the observatory from a site no longer passed on by the Daily Mail. And but one of the Board of Visitors, the civilian professor at Oxford, Herbert Hall Turner, wrote that the Board of Visitors was unanimous against the idea of moving the observatory in any way. Next slide, please. And eventually compromise was found. The astronomers at Greenwich found that a thin film of mercury eliminated the effect of engine vibrations on the star transits. I should say that the transit telescope observed transits of stars reflected in a trough of mercury. That was used to eliminate errors in observation. And the power station would in future agreed to use the newer type engines which ran using turbines rather than the old-fashioned reciprocating engines, which were much more clunkier and produced much more vibrations. And also the second set of chimneys, when built, would be shorter. So that by 1908, the LCC's acceptance of these recommendations had to a great extent averted the problems caused by the power station. And if we have the next slide, please. We can see that's the power station after it was completed in about 1911, and you can see that now that one set of chimneys is rather shorter than the other. Next slide, please. And that is the power station today, which still survives and thrives. Greenwich may no longer be much used as an active observatory, but the power station is still generating electricity, this time for the London Underground. Next slide, please. Now, Christie was succeeded in 1910 by Frank Watson Dyson, who had been chief assistant at Greenwich from 1894 to 1905, and then he'd been Astronomer Royal for Scotland for 5 years. Dyson further scaled down some of the traditional positional observations in support of navigation, and also stopped an ongoing photography project, which was to photograph the Oxford University's zone of the astrographic chart, which Oxford had never found funding to photograph, and concentrated on data analysis instead. Dyson was interested in things like proper motions and astrophysics of stars. So this was a transition from gathering more and more data to extracting some science out of it. Next slide, please. In 1911, the London County Council requested to increase the capacity of its power station, and the Dyson and the Admiralty approved this subject to certain safeguards, but the Royal Society Council, which was mostly composed of non-astronomers, said that they cannot consider it to be as yet established that the proposed extension will not be to the detriment of the observatory, but considered it not within their duty to object. So clearly there were some doubts by this stage about the effect of the power station on Greenwich. Next slide, please. Now, one man who objected to that conclusion was a council member of the Royal Society who was not present at that meeting, and his name was Arnold Malloch, and he was a precision engineer, and he studied physics in Oxford, so he knew what astronomy was all about, and being a precision engineer, he knew about exacting tolerances required by astronomical observers. Malloch opined that given that it was practically certain that no agreement could really stop the expansion of the power stations in principle, and it was likely that conditions near the Royal Observatory would only worsen with time. So he thought the present would have been a favourable time to consider the removal of the observatory to another site. Malloch suggested that the observatory be moved to Addington near Croydon, which was on the Greenwich Meridian. Next slide, please. But Dyson's response was, in my opinion, the influence of the neighbourhood to London on the observations is very small compared with the natural influence of climatic conditions in this country. The conditions at present are not such as would justify the great expense and difficulty of moving the observatory, and I do not consider that they are likely to become so in the near future. And that basically closed any idea of removing the Royal Observatory, apart from the Magnetic Observatory, which moved in the 20s. But other than that, it was not until the 1930s that Dyson's successor, Spencer Jones, seriously got interested in moving the observatory, and that ultimately led to its removal to Hurstmonceux in Sussex in the 1940s. Next slide, please. Now, this basically the climax of this early 20th century period for Greenwich Observatory must surely be the so-called Einstein Eclipse of 1919, which was to test the deflection of starlight caused by the sun's mass, as predicted by Einstein's general theory of relativity. And this demanded a very, very precise measurement, because the light of stars close to the limb of the sun would be deflected by up to a maximum of about less than an arc second, or about 1/1000th of the apparent diameter of the moon. So they had to measure that tiny angle with portable equipment in 1919. Although Eddington is the astronomer best remembered for making the crucial observations, in fact, the expeditions as a whole were organised by Greenwich. There were actually two expeditions. Eddington and an assistant went to Principe, an island off the west coast of Africa, and two Greenwich astronomers, Andrew Crommelin and Charles Davidson, went to Sobral in Brazil. And it was the two astronomers working at Brazil who got some of the best data. They had clearer skies. And Eddington and his assistant Cottingham had much more trouble with clouds. But even so, Eddington couldn't resist developing and measuring his plates while he was still on Principe. And from the one good picture he got, he could tell there and then that they probably got it, that Einstein's theory was probably confirmed. And Eddington was a great mathematician, and he was one of the very, very few people who could understand the general relativity theory at the time. But nevertheless, he was also a very good observer, and that observing experience he owed to his time at Greenwich when he had to sort of muck in with the observations, whether it was observing eclipses or doing something really humdrum like measuring vibrations caused by the power station. And the observations of the eclipse also benefit from the close connections between Greenwich Observatory and Cambridge University, which was another legacy of George Airy. Next slide, please. So just to sum up, so Christie in the late 19th, early 20th centuries continued basically the Airy tradition of utilitarian astronomy plus certain long-term programs involving non-utilitarian stellar astronomy and solar physics, using new instruments, some of which Christie purchased through the Admiralty, but quite a few of which were also donated by Sir Henry Thompson. Christie certainly branched out into non-utilitarian astronomy, but it was still mostly about star measurements rather than the astrophysics of the stars themselves. That emphasis started to switch when Dyson succeeded Christie as Astronomer Royal, and of course the Einstein Eclipse was the most famous astrophysical observations. And you might ask why, given how bad the observing conditions were at Greenwich, the astronomers themselves were not keen on moving the observatory. I have suggested in an article since published in the Journal for the History of Astronomy that there were certain cultural reasons for not moving out of London. Partly is the fact that the astronomers were used to being in London for scientific meetings, and so Greenwich Observatory was happy for that. And there were also reasons of prestige and tradition for remaining at Greenwich. So this caused a certain amount of inertia at the Royal Observatory, and sometimes people thought the original Royal Observatory would be too difficult to replicate elsewhere. So those reasons are perhaps reasons why not until the 30s, not until it became absolutely impossible to observe at Greenwich, did they finally decide to move. But anyway, I hope I've showed you that Greenwich was doing a lot of interesting things, and I've certainly found out a lot of interesting things about Greenwich in the late Victorian and Edwardian period, and I hope to find out more interesting stuff once the libraries reopen. So thank you all very much for listening. Thank you.